Hi everyone. Today we're going to be presenting our project on solar cells. My name is Zhang.
My name is Tyler Guedry.
My name is Tuyet.
And let's get into it.
So to begin, I'll be introducing the background, where we'll be talking about two quantum phenomenons, the photoelectric effect and the photovoltaic effect. Now, the main difference between the two is the photoelectric effect is a phenomenon where the light and interaction between solids, liquids, and or gases cause an ejection of an electron. Now, this was first discovered by Albert Einstein in 1905. The photovoltaic effect is described as a generation of energy when radiation ionizes in a certain area. Now you may ask, what is a solar cell? A solar cell is an electronic device that converts energy of light directly into electricity, usable through quantum phenomenons. Now, for my project, I'll be introducing silicon quantum dots solar panels. So, silicon quantum dots and perovskite crystals solar panels. Now, what they found when introducing these two silicon quantum dots and perovskite crystals together inside a solar panel is the increased conversion of energy and efficiency. So the increased efficiencies actually was measurable by 1.4% for power conversion, and power conversion efficiency was by 5.6% improvement. Now, the perovskite crystals were actually spin-coated with silicon quantum dots in different concentrations of 0.01 and 1 milligram per milliliter. The thicknesses of the actual silicon quantum dots varied a little bit from 12.7 to about 15.2 nanometers. The disappearance of the natural grains. So when the silicon quantum dots were spin-coated on the perovskite crystals themselves, the natural grains, or the cracks, I guess you can say, within the crystals themselves would actually be filled in by the quantum dots, which would significantly increase the efficiency of the solar panels themselves. So the silicon quantum dots were successfully introduced to the actual solar panels themselves, which increased the potential by 18.2 to 19.6% depending on the solar panel itself. Now, for the results, they found that when low-quality perovskite crystals were coated with a large amount of silicon quantum dots, they found that it was unabsorbed light will be reused, which would also increase the efficiency of the solar panels themselves. And so that means that they could use low-quality crystals, which means that there would be a less demand for them, and this will make the industry. This is significant implications into the industry itself, and all they have to get is the actual solar panels themselves.
Okay, so now we can talk about the photovoltaic effect. The photovoltaic effect can be defined as the generation of a potential when radiation ionizes the region in or near the built-in potential barrier of the conductor. The power is coming from the ionizing radiation. So on the right, you can see a simple model of the solar panel that consists of an N-type material, a P-type material, and creating a P and N junction. So when sunlight hits this solar panel, it will knock electron loose, creating a pair of electron and hole, which I'll cover in the next slide. Okay, so the drawing on the left side of figure 1 show how light generate carriers when entering a semiconductor. The circles in the diagram represent the atoms, and the two lines between the circles represent the valence bonds. And when a photon that is strong with enough energy to knock one of these valence bonds loose, it will create an electron and hole pair. On the right, you can see the same process using energy band model for a semiconductor with P and N type. The N type we can see at the top with many electrons, N in the conduction band, and a few holes, P in the valence band. On the other hand, P type is the opposite with more holes, P in the valence band, and less electrons, N in the conduction band. When sunlight strikes the conductor, the photons with more energy than the forbidden gap energy will produce both types of carriers in equal numbers. We can look a little closer in the next slide. Note that the depletion zone is the same thing as the forbidden gap. And in this diagram, these charges, the electron is the E minus, and the hole is the little red circle you can see it at the bottom. So when the electron and hole pair get created, that happens in the depletion zone, and these charges would then be pushed to opposite ends due to the strong magnetic field, which is represented by the blue arrows. These charges, electrons, represent the negative charge, and the hole represent the positive charge. These charges will then be collected by electric contacts at each end, and these electric contacts are connected by wires. So this creates a circuit. So the electron would travel through the wire to get to the hole on the other side, creating a full circuit with current flowing, of course.
Solar cells are usually named after the semiconducting material they are made of. These materials must have certain properties in order to absorb sunlight and depend on different consumption purposes. Solar cells can be designed for optimal uses on Earth's surface or in space. They can be made of one single layer or multiple layers to take advantages of various absorption and charge separation mechanisms. There are three different types of solar cells: first generation, second generation, and third generation. Let's dive into the first generation solar cell, which is also called conventional, traditional, or wafer-based cell. They are made of crystalline silicon, the commercially predominant photovoltaic technology that includes materials such as polysilicon and monocrystalline silicon. Here's the general structure of the first generation solar cell. Move on to the second type, which is the second generation solar cell. They are thin film solar cell, consist of amorphous silicon, cadmium telluride, and copper indium gallium selenide cells that are commercially specific in utility scale photovoltaic power station, building integrated photovoltaic cell, or small standalone power system. One specific type of second-generation solar cells is amorphous silicon. They are non-crystalline form of silicon, the most well-developed in film technologies, and have been in the market for more than 15 years. The panels are formed by the vapor depositing a thin layer of silicon around 1 micrometer thick, which is less 300% time than the traditional silicon solar cells. And the cell structure had a single sequence of thin layers, but degradation in power output in the range of 15 to 53% when exposed to the sun. So multiple layers are needed in order to prevent the effect and maintain stability. They are widely used in pocket calculators and power some private house, building, and remote facilities. Here is the pictures of the triple layer system, which is also called unisolar. Last but not least is the third generation solar cell. They are made of thin film technology described as emergent photovoltaics. Most of them have not yet commercially applied and are still in the research or development phase. A specific type of the third generation is dye-sensitized solar cell. It is based on artificial photosynthesis, which mimics the natural absorption of light energy to process and convert any physical light into electrical energy. Its semiconductor form between a photosensitized anode and an electrolyte photochemical synthesis. It is a low-cost solar cell belonging to a group of thin film solar cell. However, they are expensive due to the material and the liquid electrolyte, making this solar cell challenging to manufacture and properly function in all weather conditions. They can be used in a wide range of light conditions, indoors and outdoors, enabling the user to convert both artificial and natural light into energy to power a broad range of electronic devices. Here's the general structure of dye-sensitized solar cell. After considering the application of these two effects on different types of solar cells, photovoltaic effect is used regularly to produce second and third generation cells with a high efficiency and low cost, and the amorphous silicon solar cells are considered the best option currently.